Um, Hi everyone, thanks for coming to our first event this year. So this event is brought to you by datatalks.club, which is a community of people who like data. We host regular events, and this event is one of such events. Today we'll talk about data versioning, and today's on Tuesdays we typically have more technical events with presentations, and today is one of such events, data versioning explained. Then next week we'll talk about model monitoring, and then in February, on the 2nd of February, we will talk about Feast, which is a feature storage, like a special platform for storing features. Then we have events on a Friday, which we call live podcasts. These are without presentation, just conversation between people. And this Friday, we will have a topic about writing. We will talk about writing, why writing is important in a tech career, also including data science. Then the next week on Friday, we will talk about a role called developer advocate. We will find out what they actually do. And then the week after, we will talk about MLOps. So for questions today, we'll use Slido. I will share a link with you. And today, the topic today will be data versioning explained. And Itai will talk about this. And Itai is a software engineer at Traverse, which is a company behind lakeFS. This is an open source platform that delivers resilience and manageability to open storage-based data lakes. So you will find out more about this and about data versioning. So now I am stopping sharing, and the floor is yours. And I will quickly, I will also put the link to Slido in chat. So if you want to ask anything during the presentation, just click on this link, ask, and then at the end, during the Q&A session, we'll go through these questions. So please, Itai, start.
Thank you, Alexei. Can you see my screen?
Yes.
Okay, so thanks, Alexei, for hosting this event virtually, and thank you everyone for joining. So I'm Itai Admi. I'm a software engineer currently working for Traverse, which is the company behind lakeFS. And I've always worked on platforms and tools for fellow software engineers and currently data engineers. And I think that's what excites me the most. We'll talk today about what is data lake versioning and why do we even need that. Bear in mind that I work for Traverse and I'm a little bit biased, but I guess that's okay because everyone is biased in one way or another. Okay, so today we're going to have a brief overview of the use cases for data versioning. There are a lot of tools out there that claim they do data versioning, and they all mean slightly different things. Then we're going to move to talk about lakeFS and how do you use that, and how does it work in compare to other tools. And we're gonna dive a little deeper, even see a demo of lakeFS and talk about lakeFS architecture and the design choices we made and why we made them. Okay, so these are the use cases for data versioning. It's not easy to put them in 4 little boxes like that. Of course, there are probably some use cases that I will not mention, and there is probably some overlap between those 4, but that's our version of the use cases. So the first one is collaboration, which basically means how do I share data between data scientists and how do I share code that allows me to do useful things with that data. Another use case is ML pipelines or everything that relates to machine learning operations or built-in those pipelines. Mutability and concurrency control tries to handle the update of data. Basically, I have tables that I want to update or mutate. which is not an easy thing to do when we talk about modern object storage. Object storage. And the last one is where lakeFS fits in. It is the data lifecycle management. You can compare that to application lifecycle management, which is everything that is around the data itself, from the research to production. If you compare it to code, so you run a little experiment with your code locally, all the way until you ship it to production and that code runs and is exposed to your customers. Okay, so the first use case, collaboration. So you provide a versioning as a collaboration environment for mostly data scientists. You use these tools if you want to cooperate with people globally or within your organization. Now, all the tools here are rather new and are not as mature as the next tool that we're about to see. So if I'll go over them one by one really quickly, you have Dolt Hub, which is a hub that built on top of Dolt. Dolt is the version DB, which is kind of an SQL database, but it allows to do some crazy things. It holds versions for the row or even for the cell level for each cell in the database. And Dolt Hub on top of Dolt gives you a collaboration environment that tries to do everything in one tool. Kaggle gives you a platform to share public data sets, and it also exposes a notebook, like a Jupyter notebook environment, where you could also share code. There are also some competitions between different AI models, and Kaggle gives you a platform for these kinds of competition. I saw today that they have a competition for the best Rochambeau AI algorithm, whatever that means. And you can use Kaggle to share code in the notebook environment. The last one is Duds Hub, which is an Israeli company. It's built on top of DVC, which we'll talk about soon when we see ML tools. It is focused on machine learning, and it gives you versioning on top of your sample data, on your metrics, on your parameters for your models. And DugsHub tries to be your GitHub for the ML models and for your machine learning pipelines altogether. And it exposed a collaboration environment like you have with GitHub for code, so you can comment and visualize and interact on top of the models. So next use case is the ML pipelines. It is, of course, centered around machine learning. It is by far the most developed category. There are dozens of tools out there that try to handle this, this use case. They allow you to take an idea all the way. If you have some machine learning models and you want to test it locally, and you have your data set, and you want to manage the experiment pipelines from several perspectives. And data and data sets is only one of those perspectives. So I want to mention out the DVC tool out of the rest. DVC integrates into your code Git repository, basically, and it stores link within your Git repository. Basically, those link points to an underlying data set that can be stored in your favorite object storage, whether it's S3 or Google Cloud Storage, or even shared server within your organization. And you gain the versioning by the Git repository. So you could actually see the dataset links changed as part of your Git repository, but DVC does more than that. It also adds you the capability of pipelines. It knows how to compare metrics between different commits. I'm talking about the machine learning outputs, like the model outputs. And also it has some language of workflows that you could write a custom integration test inside your Git repository to be run by DVC. Okay, the next use case is mutability and concurrency control, but let's start with the problems we have with object storage today and the way we use them. So object storage files are immutable. Basically, it means that you cannot change an existing file. You can only write it again. And modern object store will allow you to append, but if you're looking to change or delete an existing row from a file in object storage, this is simply cannot be done today. And basically, if you're talking about OLAP, where you're not interested in reading a single row, you're interested in reading the entire data and then doing something useful with it, then you'll probably store your files in a column compressed manner, which basically means that a row is split between multiple column files. And if you want to change or delete that row, then you need to go and change multiple big files and rewrite them all the way, actually fetching them, getting them to your local environment, deleting that row, and then storing them back. So there are several tools that try to handle these problems. Let's first talk about Hudi and Delta Lake. They are the big competitors, and they kind of try to solve it in the same manner, in such that they keep in your object storage small delta files, and which represent the change that you made to those files or to those tables. And every once in a while, they'll take the base file, like the base Parquet file, and apply all the changes on top of that. And therefore, you'll get a new version of your data, and the version control is kept in a linear way. You get the new version, and you could go back in time to read the previous versions. So we also have Iceberg, which is a project that originated from Netflix. Now it's an open source. They took somewhat different approach by holding manifest files that point to your existing file in the object storage. And every time you change something, then you create a new manifest file. And the root manifest file is actually your snapshot. And the version control is kept by storing those manifest files. So you could simply traverse those manifest files if you want to go forward and backward in history. Of course, when we talk about concurrency and how we update concurrently those tables, then there are several approaches. Hudi tries to do it like we do in DB, in databases, with an MVCC control, and Delta Lake, I think, haven't resolved that yet. They do plan on doing so in their next version, but I think that for now, you can only use a single Spark drive. So now we're moving on to the fourth use case where lakeFS fits in. So the data lifecycle management. Basically, this is the use case which lakeFS focuses on. It provides you with a tool to treat data like we treat our code. So the process starts when you experiment locally with the data, and it continue all the way until it reaches production. And it allows you to do that in a safe and an isolated manner and with lowest friction as possible. So it's an atomic version data lake on top of object store. Let me try to break it down a little bit. So lakeFS enable you to manage your data in the same way you manage your code, right? We have the best practices we learn from software engineering, and we want to take those and bring them into the data management world. How do we do that? We add Git versioning and semantics on top of your existing data lakes. And you can think about it like it transforms your object store to a Git-like repository. So let's have a quick glance on how we plan on to achieve that. So it's a manageability and resilience layer. We don't try to compete with the object storage or introduce a new table format like Hoodie or Delta Lake does. Um, we wrap your existing object store, and basically you could think about the lakeFS or the lakeFS server as a middleware or a proxy layer that sits between the applications you have and the object stores. So your data sources, whether it's Kinesis or Kafka or Apache Storm that um, sends or writes data to your object stores, and your readers, the consumptions, the consumers, whether it's some Spark job or Athena or anything else, they can continue to read and to write to the object store while talking to lakeFS without them knowing. So we are actually agnostic to the readers and the writers, and we allow the user to do smarter things with the management of the data. We want to leverage the existing capabilities of the object stores by by keep using the object store, right? The object stores today are easy to use, they are cheap, they are scalable, they are resilient. I think that S3 durability is like 12 nines, which is amazing. And we want to keep using that features and without harming the scalability of the underlying storage. So as I said, it's API compatible with S3. We have an S3 gateway. It allows your existing application to keep using the object store the way they did before. You don't need to change everything with the way they work today. You simply need to point them to a different endpoint. But we do have metadata. We have the Git metadata, the commits, the branches, maybe the duplicate files that you have in your data lake. And all of that is currently camped in a versioning engine. Currently it's RDS, which allows you transactions and atomicity and isolation between concurrent readers and concurrent writers. And what you gain here is the full Git semantics. You get the branches for your data, you get commits, you get merges, and we'll see several use cases. So you could ask, how do we even branch data? How do we handle, what are the use cases? This is some example I found of branches from some repository that I won't tell its name right now, but it looked like the strategy here is create as many branches as possible. So let's talk about branching data and what are the use cases and how do we do that. So the first use case is the development environment for data. So if I'm a developer, I want to be able to experiment with the data. I want to try new tools and maybe change existing workflow without it affecting the consumers that read directly from the data lake in production. I want to be able to reproduce. I want to be able to go to any point in time when I know that my data was valid and my code was valid, and to have like a good point where I can always retest things. And I want to compare. I want to run several experiments and to test the outputs of those. So today you could probably achieve most of that if you copy the data and then try and run your tools and point them to that new prefix location that you created for the experiment. But then a bunch of questions arose, like what happens to retention? Why do I waste space in my data lake? Who cleans that up? Can consumers still see that prefix, that location? What about permissioning set for that location? So you could achieve better isolation if you use lakeFS on top of your existing data lakes. So the first example is the experiment. Let's say I have some experiment. Let's say I want to upgrade to Spark 3.0, and I simply branch out. You could see the lakeFS command. I simply branch out from master and I create experiment one branch. And then I change my existing code to use the new Spark 3.0 driver. And I point existing workflow to run using the new branch. Now, sometimes things fail or I see that they are about to fail and I kill them halfway through. Then I'm left with some garbage objects in my data lake. So I could simply revert that branch and all the files that are stored in that branch that weren't committed will simply be deleted from my object store, and I could reiterate. I could try back and forth until I'm happy with the result. Simply delete the branch, and I know that every single object that was created inside that branch is now gone. Okay, so another thing is that I want to be able to compare. So let's imagine that I want to test two compression algorithms like Snappy and gzip. So I simply create two branches, experiment one and experiment two, run different code on those branches, and I simply diff the results. I have the lakectl diff command that allows me to compare the two commits from different branches. I want to know how long it takes it to run. I want to know how does it affect the read speed. And I also want to know the size of the resulting objects. So I may create like 20 different experiments and interact and compare between all of them. And once I'm done, I'll delete these branches and their changes will be cleaned out. Now, I haven't mentioned that before, but creating a branch is a pure metadata operation done by lakeFS. No existing data in your data lake is being copied or moved around. This is a no operation for lakeFS. Okay, so let's imagine that I did switch to Spark 3.0 and now it is misbehaving in production. And I want to test a fix, but I want to be able to test that in a point in time where I know that data was valid without running it on the current state of the data lake, which may be bad. So I could simply revert the master branch, or I could create a new branch with the previous good known location, like good known commit, test my fix on top of that. And if everything worked as expected, I could simply revert master to the last good known location and check in my code fix. And what I have is that I know if that point in time where I have the git commit hash and the lakeFS commit hash, I know that I'm guaranteed that this situation will always last for this combination of the git commit hash and the lakeFS, which represent the data lake state. Another use case for lakeFS is the continuous data integration. So like we have today with continuous code integration, you could achieve the same with data. So with code, with every merge or with every PR that tries to merge into master, you run your GitHub action or some Jenkins workflow that tests the new code. You could have the same with data. So imagine you try to ingest new data from new stream and you want to do it safely without harming the consumers in production. Maybe your organization has some best practices that you want to continuously enforce, and we'll see an example for that in a moment. And even you could validate the metadata. You want to prevent any breaking changes from actually reaching master branch or whatever your production branch is. And you could have a point in time where you check those breaking changes. Like imagine that someone tried to delete a column from an existing table. You could simply have a point in time where you check for breaking changes. So this is some best practices that I gathered. There might be more. The thing is that we can codify the best practices in our organization and the rules of the game, you might call it. And you know that the data is available on master if you follow these rules. So several examples, you don't want any PII data to be anywhere except a private folder in master. Imagine you have some private prefix that is enforced, you have your permissions all set for that, and only the readers and the writers that are allowed to touch PII data can do that. So you could make sure that no new data is merged into master if it starts with the user prefix. You also can enforce the type of files that you store in your object storage. You want chip or cat files. You don't want any random CSV files, which is bigger than your average Parquet file to be merged into master. So again, you have that point in time when you can prevent these things from happening. And as I mentioned before, you don't want any backward compatible, non-backward compatible changes in your master branch. So you could enforce that as well. And if you have some metadata repository, Hive or Glue, you could make sure that the metadata resides there before you merge the data. So this is the simplest example. You have some new data stream that you test on some side branch inside lakeFS, and you're satisfied with the change and you want to merge it to master. But now the pre-merge hook ran and it noticed you tried to merge some random CSV file into master and it fails your merge. So this is really hard to achieve today in modern data lakes, since you don't have that point in time where things enter your data lake. Basically, everyone with permission, any tool with permission can read or write to your object store without you having the ability to enforce. Another use case for lakeFS is the continuous data deployment. So I want to guarantee the data quality that I have in production. Remember that data is always being written and there's a need to continuously check that quality of the new data that is being written. I also sometimes want to check intermediate results, like I have Airflow or anything else, a big chain of jobs that run on top of my data lake, and I want to be able to fail that without having intermediate results in my data lake. And I want to be able to revert bad changes on the spot like we've seen before. So this is an example. Let's say you're streaming data with Kafka Connect, and you commit to that side branch every now and you then merge it to master. So you can test the quality of the stream before it reaches your master. And this is a really strong guarantee because now readers and masters know that the data they read is safe to use because you tested before you merge it to master. Also, if you notice that there's a point in time that something went south, that the data had a bug in it, you could always go back in time. Right here, we do it with the Kafka offset. If you know that from some offset, the data had some bug in it, and you use the lakeFS commit metadata, then you could simply point back and revert the changes that were done to your code, to your data. Another example is you want to test your data qualities. So there are some really good tools to achieve that today. You have Monte Carlo, you have Great Expectation, which is an open source. But the thing is that they will run on your existing data lake, might which might already be exposed to you, to your consumers. So again, using that pre-merge hook, you could point your script to be run every time that your data is being merged to master and is going to be exposed to your consumers, and check the data quality in that point in time. Okay, so I've shared a bunch of use cases. Let's go and see some demo of lakeFS. Maybe it will help you understand a little bit. Um, let's see if it works. Now I need to refresh it. Well, it's loading if you're unfamiliar with Katacoda. So Katacoda provides a really cool environment for running tutorials. And I will simply click on a few buttons and the commands will be executed. So we have here an environment where lakeFS is set up and running in a container inside their inside the Katacoda virtualization layer. So lakeCTL is the CLI tool that allows you to run commands and play with lakeFS. Of course, we also have an API. So basically, if I do lakeCTL help, I see the bunch of commands that I can use with lakeCTL. And let's go ahead and create our first repository. So I created my first repository, named my repo, and I created with a local storage. Files will be kept on this machine. If I list the repository, I can see that my repo was just created, and I have my default branch name, which is master. Okay, let's move on and play with some file. Again, I will use the lakeCTL CLI to upload the first file. I have some files stored locally, and now I import it into the lake. I upload it into the lake, and I see that that command succeeded. Now there's another option here to upload using stdin. I won't go into that, but let's use the listing command, which is similar to the S3 listing command. And we see that I have some prefix there, the IMDb, the file that I was just uploading. And if I look even further, I can see the actual file. Now, there's a lot of things I can do with the lakeCTL. I could see some statistics on that file. I could remove that from the object storage. Or if I'm satisfied, I can go ahead and commit this file. So let's go and commit and create my first commit, and I see that worked. So I created on the master branch my first commit with that file. And if I look at the lakeCTL log command, then I'll see all of the commits. So first the repository was created, and then there's the first commit. There's the initial import branch that was created. Basically, if you want to work with lakeFS and have some existing data lakes, then we have some infrastructure to do that. You simply import your inventory, and we won't copy all your data. We simply hold links to your existing data lakes objects. Okay, let's see a Spark example. So let's create a branch. I could test Spark on top of that. It's called my branch, very original. And let's see that it was created, and I can see my branch. I'll open Spark shell. It will take a moment. And then I will immediately run the Spark script. And while it's running, I'll explain a little bit about the S3 gateway and how we point our Spark jobs to use the lakeFS instead of S3. So while it's running, it will take some time to read and to process and to write that data. Look at the work there that I'm pointing it. I'm still using an S3 path, but instead of calling the file directly, I now have a repo and a branch that I'm working on top of. And I point my S3 endpoint to be the local S3 running locally. And that's all it takes for your existing Spark jobs to work on top of lakeFS. Now the application is done reading and it's writing the output objects into lakeFS. Let's wait until it finishes. It is usually faster than that. Maybe Katacoda has some problems with the bandwidth. Okay, it is now finished. Let me exit the Spark shell. And let's look at the differences of my working, of my stage files on that branch. So I run a diff command and I can see a bunch of files that are currently not committed in my branch. Okay, I could look at them. I could maybe run different tools to validate them. And once I'm satisfied, I can commit those into the branch. Okay, and I see that the commit succeeded. And now I have my files on that, on the files, the objects committed on that branch. And I can, again, diff the files with master. So I'm diffing two branches, my branch and the master branch, and I'm expected to see the files that were changed between the two versions. Now, sometimes master change while I work. We know that from code. I want to bring master into my branch and work on the newest version of master. And once I'm done iterating on that, I could simply merge my branch into master. Okay, and it worked. Let's look now at the log of master, and we can see that the new commit, the after Spark job commit, was successfully merged into master. So that's it for the Katacoda demo. Now I wasn't able to show you the UI using Katacoda, so I ran lakeFS locally too, and we can explore that a little bit. Now, if I look at master, these are the current files I have in master. If I look at my branch, I have two test files. If I look at the current changes in my branch, I see that I've added a new file, but I haven't committed it yet. So I will write now the test file and commit that. And when I look at the commit for my branch, there's this right here, the commit I just created. I can compare between the two branches. So I want to merge my branch into master, and there is the change set of the files that want to be introduced into master. And if I'm satisfied with the test, I could simply merge that. And when I look at master now, I could see that file exists there. So again, wrapping all the use cases we saw into the UI demo and the Katacoda demo. Let's move on and talk a little bit about the architecture, and then we could have some Q&A. So the architecture, this is the current one. So you have the lakeFS server and the RDS metadata instance, which is Postgres for now. So you have your existing application. There could be Spark, Presto, or any other data consumer and producers, and they talk directly to lakeFS and they store data through lakeFS. And lakeFS does two things. First of all, the servers go and store the file in your object storage, if it's S3 or anything else, and it keeps the metadata in the Postgres instance. Only then it will report back to your applications. So lakeFS server is stateless, and you can create as many as you want to support your throughput. But the RDS obviously cannot be duplicated, And if we talk about really big data lakes, we talk about petabytes of data, and we talk about hundreds of megabytes throughput, then we need something stronger than that because the RDS instance becomes our bottleneck. So we moved on to the next version of lakeFS architecture, which is basically moving from metadata storage to our RocksDB, which is backed by S3. So you have your Spark or Presto, and we've written an lakeFS Hadoop client or an SDK, and that SDK does two things. First of all, it goes and stores your objects directly in the object storage. It doesn't go through lakeFS. Then it will update the lakeFS metadata manager, which will save the state. If you have any other consumer or producers that don't have that client, they can continue to talk to the lakeFS gateway, which will store the objects and then update the metadata manager. So the entire metadata is kept locally by an RocksDB and being periodically synced into S3, which gives you two things. First of all, if lakeFS is down for some reason, you can continue to read or write using the metadata that is stored in S3. Second of which, it allows you to get rid of the bottleneck that we had with the RDS instance. Okay, so that's all the resources I had. I will share the deck with Alexei to send it to you guys. We have a bunch of documentation. You can join our lakeFS channel. You could go and check out the code. We're open source. Remember that the best and easiest way to contribute to an open source project is by simply starting the repo. And if you have some time and you want to contribute, we'll be more than happy. I think that's it. Any questions?
I have some problems with my computer, so if you want to ask a question, because I don't have access to Slido right now, I needed to reboot it. So maybe if you have any questions, you can just use Zoom to ask it. Yeah, maybe while like maybe if somebody else has a question, I do have a question. So I understood that to run it in Spark, what we need to do is first put the branch where we want to write in the path, right? So it's bucket name, then branch name, then our usual like path, and then we also need to use the lakeFS endpoint, right?
That's right.
This is in Spark. But let's say if we have some custom job that we wrote in AWS batch, or I don't know, a job that we run in Kubernetes, or like something else, not Spark. What do we do in this case? How do we write our data?
So I tend to split those use cases in terms of what you just asked me into two. First of all, if you are able to configure your client or job or whatever to a new S3 endpoint, then you can simply use the lakeFS endpoint that you use to run your server. And if you don't, so it really depends on the tool. We have some workarounds if we talk about AWS about Hive or AWS Glue, then we kind of have some symlinks. It really depends on the use case, and if we have a lot of documentation per use case, and if something is missing, then I'll be more than happy to understand the new use case and see where we could help.
Okay, I rebooted my computer, so now I have access to Slido. So Amir is asking a question. Would you run experiments by comparing the output of two different branches? Would this be a better practice compared to running experiments on a single branch?
Well, it depends. If you run the two experiments on the same branch, then diffing kind of becomes a problem. So I would always try to compare to what we do with code. If you want to compare files inside a single branch, then it's probably a hard thing to do using Git commands. But if you have two branches or two separate commits that you want to understand the difference between them, then it's easier. So to the question that you asked, I believe that using two separate branches is the way to go here. But you could use the same branch, commit, and then use the root commit of that branch to create another commit. You could do a lot of things like you do with Git today.
Thank you. So I'm just wondering, like in this case, in this situation, when we have two different branches and we have two different, I don't know, like one colleague is running one change, like one job with one change, and then somebody else is running something else. And then in Git, we know how to merge, but like I'm still trying to comprehend, to understand how we can do it with data. Like when we have two Parquet files, like how do we actually merge them? Or it's not possible. We just need to merge first the code and then rerun it.
So lakeFS tries to be agnostic to the content that you write. It tries not to care about the actual file content. If the file was changed even with 1 byte, then we'll show it as a diff between two different branches. And if one of them was already merged to master and you want to merge another one, then you'll have a conflict. So unlike Git, where it makes sense to try and merge files that like code that was changed in different location, for looking at big data sets, it makes less sense. And if lakeFS is unaware to the actual underlying content, then we'll show a conflict, and it's up to the user to decide what to do with those files.
Yeah, makes sense. So it's probably too difficult to even imagine how you can compare two binary files, right? Like it's just simpler just to let users know, hey, there is an issue, just do something with this.
Yes, and actually, when you don't know the content of this file, trying to guess on behalf of the user is really error prone, and we recommend that he'll use his existing tool to diff between the files and then make a decision.
Okay. Yeah, thank you.
Okay. Anything else? Okay, great. Thank you, everyone. Thank you, Alexei, for having us again. And I will share the slides with you, and you could share it to everyone else.
Yeah, you can just put it to the events channel in Slack.
I will.
Yes, thank you, everyone. Yes, see you in Slack.
Thanks all.
Goodbye.
Bye.